question is from Nelson Physics 12, page 211, number 11. It's a conservation of energy question that involves a spring. So you now have elastic potential energy in addition to gravitational potential energy and kinetic energy in this question. What you have is a block on a ramp being fired up the ramp by a spring. We've got some information here we'll need about the mass of the block and the spring constant for the spring. We'll come back to those at the end. The first question we need to answer is if the block is to slide up the ramp through this vertical height, 5.7 centimeters, how much do you have to compress the spring at the bottom so that it will fire the block to exactly that height? So we will begin, as always, with a system diagram where we can label everything that we know and need to know. Okay. So let's draw our ramp nice and large. Our first position of interest is when the block is down here at the bottom, being held by a being held against a compressed spring. So the spring is let go, the block goes up, up, up the ramp to this final position, which is 5.7 centimeters higher than its initial position. So we can label our positions A and B and start filling in things that we know. Well, as usual, we say that the lowest height in the question will be our h equals 0. So our starting point, h is 0. And we're told in the question that it's gone up the ramp a vertical distance of 5.7 centimeters. And we'll put that into meters. It will be released from rest after compressing the spring. So V here is 0. At the maximum height, after it's gone up the ramp, it slows, it slows, it slows before it turns down or it falls into its hole, but it's reached its maximum height again. So V is also 0 at the top. Then finally, because we're dealing with the spring and the elastic potential energy, we need to know how much the spring is compressed. And that, in fact, is our unknown for this question. Part A says, by how much must the spring be compressed? After it's left the spring and gone up to the top of the ramp, compression of the spring is not a factor anymore. So X is 0 there. All right, that looks fairly well organized. So now we can move on to our energy bar charts, or LOL diagrams. Okay, so there we go. And we start by defining our system. We have this small block. There is a change in height, so it's interacting with the Earth via the Earth's gravity. But we will also include in our system the spring. Now the spring does work on the block when it's released from its starting position. One way of treating this question would be to say, okay, I've got work input from the spring. However, by including the spring in the system, we can instead just add a bar to the chart which is for elastic potential energy, and then it's taken care of there. So we will have an additional bar, as well as EG and EK, we will have a bar for the elastic potential energy. So these three types of energy will add up to the total mechanical energy. At position A, gravitational potential energy is 0. Kinetic energy is 0. So the only type of energy is our elastic potential energy. At the top of the ramp at the maximum height, there's 0 elastic potential energy, 0 kinetic energy. The total energy will be the same here because we have nothing added or subtracted. That's the effect of including the earth and the spring in the system. So our total energy is the same. And all of that energy is gravitational potential energy. Now, with our LOL diagram complete, we can move into the energy equation. The total energy at A is equal to the total energy at B. At position A, all of that energy is elastic potential energy. At position B, it's all gravitational potential energy. So EE is a half K X squared, compression at point A. The gravitational potential energy at B is mg H at B. So we can substitute in. We know all these values except for the thing we're trying to solve for. K is 9.5 newtons per meter. The mass of the block is given as 3.5 times 10 to the minus 3 kilograms. And we put in our value of G. And the height at B, the 5.7 centimeters. And this solves to give you compression at A is 0.20 meters. To recap then, the only difference between this and other questions that you've done is that you now have an additional type of energy, which is your elastic potential energy. System diagram is the starting point. Draw your positions clearly and label your givens. LOL diagrams now have an additional bar for elastic potential energy. You still just put all the relevant forms of energy into the energy equation, substitute what was given, and then solve for your unknown. Now, part B of this question asks, if friction were not negligible in this case, if it was experiencing friction as it went up the ramp, what would happen to your answer to A? Would the amount of compression necessary here increase, decrease, or be the same? And then of course you have to explain it. And that's a problem that you might get and have to solve actually. And to talk about that, I want to refer to your LOL diagrams. If you're experiencing friction but you still needed to get the block to rise up to the same height, your LOL diagram in B would be exactly the same, because this is how much gravitational potential energy the block would have to have in order to reach the given height of 5.7 centimeters. But what would be different about this is that you would have thermal energy exiting the system on account of the kinetic friction on the ramp, which means that your new energy equation would be the total energy at A minus the thermal loss is equal to your total energy at B. That would mean then that whatever that Q value is, these bars would have to be that much taller. You need more elastic potential energy at the beginning of the system because of the losses that you're going to experience due to friction, and for more elastic potential energy, your compression, your X value, would have to be larger. So the answer to B is it would increase, and the explanation is along the lines of what I just said. So that's how it works. Go try some of your own now. Good luck.